My name is Kevin Stroski. I just completed a 6-month internship at the U.S. Department of Agriculture with the previous speaker, Yelena Sapoznachkova, and I'm here today to talk to you a bit about the non-target work that I did related to food contact materials and PFAS found within. As can be seen by this figure by the ITRC, per and polyfluoroalkyl substances, or PFAS, can include compounds that are both polymers and non-polymers, as well as a wide array of different substances found within those base groups. However, similar to discussions of who is the greatest basketball player of all time, classifications of whether or not a substance is a PFAS greatly depends on the definition used. Early definitions required a CF3 or C2F5 group, as in Buck et al. 2011. However, more recent definitions have expanded this, where the OECD guideline, which has the most broad definition, requires either only one CF2 or CF3 group to be classified as a PFAS. While PFAS have been used in commerce for over 50 years at this point, food packaging became more of a recent issue due to the shift away from single-use plastics towards more recyclable and biodegradable products, which are typically made of paper and cardboard. These products require a grease and oil resistance, and due to the inherent properties of PFAS, it can provide those resistances quite easily. Furthermore, only a small percentage of PFAS have analytical standards which can be used to generate targeted methods to analyze these materials. And many of these standards that do exist are for legacy PFAS, which are being phased out due to regulations from both European and North American regulatory bodies. So, what is a solution to this problem? One of the solutions, and the solution that we ended up using, is non-target analysis. Now, non-target analysis utilizes high-resolution mass spectrometry instruments to generate thousands to hundreds of thousands of features per sample, and then programs are used to filter those features down into potentially new substances that were not previously measured. Now, this can allow us to look at not just the tip of the iceberg or those targeted substances which have analytical standards, but also all of the potential compounds that are hiding within the sample as well. The field of non-target PFAS analysis has blown up in recent years, with many studies introducing new and exciting ways to try and identify PFAS which may have previously been unknown in certain substances. And many of these studies were the basis for a lot of our work in this project. So, our goals for this project were to develop and validate workflows which can filter those tens to hundreds of thousands of features into usable data and validate those for non-target PFAS identification, and to then use these workflows to investigate PFAS which may be present in food contact materials. To do this work, we utilize liquid chromatography systems in tandem with both Q-Exactive and Exploris 120 Orbitraps. These systems were utilized to generate the raw data for all of our samples, and then Compound Discoverer was the program used to filter and analyze the results. Within Compound Discoverer, and really any program you're going to use to analyze non-target data, you have to generate a workflow which will take your raw data and convert it into a usable, more visually appealing output that you can then do your analysis with. Now, within each of these nodes that you see have a varying number of different settings that you can adjust, and by adjusting those settings you can change both the numbers of features and the types of features that you end up getting in your output. You can also, once features are generated, compare them to different lists, as we have done here, where we look at both the PFAS NIST suspect list, the EPA master list, and the TSCA list, which has those over 10,000 compounds that we saw earlier. Once the workflow is run, which can take anywhere from an hour for 1 or 2 samples to a couple days, if you have a large number of samples that are all full of potential features, you end up with a workflow that looks something like this. Now, in this workflow, we ended up with around 25,000 potential features, but as you can see, we are currently only looking at 52 of those. And the way that we do that is by utilizing filters within our post-analysis system. So the original workflow can be adjusted to change how many features are actually detected, and then filters can be used afterwards to filter down those features into the types of ones that you are actually looking for, which in this case was PFAS substances. So this is very important because manually going through over 25,000 features sounds awful, and I don't think I would ever get any work done if that's what this entailed. So designing and testing workflows and filters to be able to identify PFAS is extremely important in the field. We went about this by spiking samples with the 34 targeted analytes that Yelena used in the work previous, and this was useful because, as you can see, many of these analytes have slightly different physiochemical properties and as well as structures. So this gave us a good broad grouping of PFAS to test our different workflows on. Our first workflow that we ended up testing had very broad features, including a low signal-to-noise ratio and a low peak rating. This was to test just how many features we could find, and as well how many of those PFAS that we spiked in we'd be able to see within this. We ended up finding around 22,000 features after the workflow was run. We were then able to filter this and remove around 99% of those features to get it down to 152. However, if you'll remember, we only spiked in 34 PFAS, so we then had to manually go through all 152, and we were able to find 30 of the 34 that we spiked in. This corresponds to a true positive rate of 88%, which is the 30 over 34 that we were able to find, and the remaining 122 relate to this false positive rate, which are compounds that we did not spike in, but were still present after both the workflow and the filter. This may not seem like an issue right now when we're just looking at compounds that we know are in there. So in this case, we're just looking for the 34. We can scroll through pretty quickly. But when we're running real samples, looking at compounds that we don't even have standards for, it can become a real issue if you have to go through very heavily and do a lot of analysis on all 152 potential features when there are only 34 actually present. So we ended up adjusting different workflows, including increasing the peak intensity, changing the signal-to-noise ratios, and adding in a M-CO2 minus H preferred ion. And this had the effect of both greatly decreasing the false positive rate. However, we also ended up decreasing the true positive rate, or the amount of those 34 PFAS that we were finding. So to help with this, we ended up going to other sources. The first source that we ended up using is something called retention time prediction. This has been previously shown by our lab to reduce false positive rates by up to 75%. And how it works is by plotting the retention time of the 34 targeted PFAS that we know are in there against the molecular weight, log KOW, log P, and log D of the corresponding compounds. We can then generate these relationships, which are seen here, and use them to compare to the retention times of the features that are in the output results. As you can see, the log P and log D relationships were less significant, so we ended up using the molecular weight in the top left for much of our results. Next, we ended up using something established by Kaufman et al. 2022, who utilized the inherent negative mass defect of a lot of the PFAS substances to their advantage. So for those of you who need a bit of a refresher, mass defect is the difference between the integer mass and the actual exact mass. So as you can see, for fluorine, we actually have a negative mass defect as we go from 19 to 18.9984, whereas hydrogen has a positive mass defect. What this means is that many non-PFAS substances will end up having a positive mass defect due to their many CH2, CH3s, whereas PFAS, like this substance here, have many of those hydrogens replaced with fluorines, and we then end up with a negative mass defect. What Kaufman did is they related this to the mass over carbon to the mass defect over carbon, and showed that in this window over here is where a lot of PFAS can be found due to both the negative mass defect and the high mass to carbon ratio. The final thing we ended up utilizing was something called compound class matching. Now, in a lot of softwares that are being developed, including Fluoromatch, which is an open source software, MS2 fragments are the most important thing to identify PFAS with, and there are many common fragments between PFAS. So this can include things like C4F9 and C3F5, or different breakdown products, and these have been implemented into different compound class libraries within Compound Discoverer. What this allows you to do is, in MS2 data, the system will look for any of these potential matching features and will show you how many of these potential PFAS breakdown products are present within your MS2 spectrum. By combining all of these features into our filter and workflow system, we were able to find all 34 of the 34 PFAS spiked, giving us a 100% true positive rate, and we were able to reduce our false positive rate down to 24%. While it is unlikely to get this false positive rate down to 0%, we find that 24% was quite good and left us with only 11 features which were not present in our sample. Following the validation of this workflow and filter method, we then sought to use it on the same 88 consumer and packaging samples that we did targeted analysis on and what was presented in Yelena's talk previously. After our analysis of all of those samples, we were able to find around 41 potential PFAS features in our output, and we split them up both between material type and food type. What you can see on the left is, by breaking it down in materials, there are 9 unique potential PFAS features found only in the paper samples, and as well there are actually 8 right in the center there that are found potentially in all 4 of the food material types. A similar thing is seen in the food types, where there are also 8 compounds found at the center, which indicates a potential homogeneity of some PFAS between different foods and food contact materials. It's important to note, however, that the confidence that we may have in each of these features might differ. So this idea was initially brought up by Szymanski et al. For broad non-target analysis and was later expanded upon for PFAS by Charbonnet. What they describe are different levels of confidence based on the amount of data that you have for each of these features. So for example, if you just have what is called MS data, or the base peak, so a peak corresponding to the full mass of the substance, then this will be likely a low confidence level 4, level 5 feature. However, as you get more, so as you get breakdown patterns and fragments that make sense and confirm the potential structure, you then increase your confidence in each of these features. The highest level, level 1, is being confirmed by a reference standard, so this would be purchasing a standard that is available for your potential feature, and then running that and comparing the retention time and all of the MS data and the high-res data that is available. When it was expanded into PFAS, they brought in a lot of these elements of the homologous chains. So in a lot of PFAS, we have these CF2 chains. So that was a potential thing that was brought in, and as well matching fragments from some of these libraries that exist. So those libraries that I brought up earlier, the more of those features that you match, the higher the potential confidence that we may have in that feature. So what I will talk about now is two different case studies from my results and how they relate to these levels and the confirmation of them eventually being both level 1 and confirmed by reference standard. So the first thing we're going to take a look at is something that in-house we dubbed the snowflake. It is a 7-member ring that is nearly fully fluorinated, and initially this was what the structure that was given to us in our output from Compound Discoverer. Now, on the left, what you can see is the retention time and peak that is generated from the LC for our MS1 data. And then in the center is the fragmentation of that same peak, generating a breakdown pattern or MS2 data. So that's how I refer to them going forward. One thing that gave us confidence that this might be a PFAS structure is in the breakdown pattern, we see these consecutive losses of either CF2s or C2F4s. This is a pattern that has been seen in many other publications of non-target data and of MS2 breakdown data. So this was some confidence that this compound might actually be a potentially new PFAS found in food contact materials. However, one thing that gave us a little bit of pause was the difference between this base peak, which is at 292.98, and the next peak at 242.98. This difference of 1 CF2 seemed like a difficult thing to break off of a ringed structure, just based on organic chemistry and all of those types of rules. So what we did is we ended up looking around at other people's work to see if we could find anything similar. Initially, we came across this really interesting paper by Hensema, which used fragment ion flagging, or basically looking for these breakdown patterns within the data to then back generate potential PFAS structures. And the thing that we saw within there was we found both the 292 and 242.98 peak within one of their potential structures that they identified. However, we did not see this characteristic pattern that we had seen in our breakdown structures. So while we got a little bit of confidence that this might be coming from a more chain-like structure, we did not find something that was exactly similar to ours. So we kept looking. What we ended up finding was a really interesting paper by Harris et al. Looking at suspect screening PFAS in cosmetics. One of the substances that they were able to identify and confirm with reference standard was 8,2-FTUCA, or fluorotelomere unsaturated carboxylic acid. The structure is at the bottom. It is similar to some legacy PFAS, but then has a unsaturated carbon and a in between the carboxylic acid and the fully fluorinated chain. Now, what we saw within this was the same characteristic pattern as our compound, and we found the 242.98 breakdown. We did not see the 292.98 though. What we did end up finding though was we saw 392.98, and not only that, but also 456. And what was seen was both of these were seen in the MS1 data, but were not seen within the MS2. So what we thought might be happening is potentially our compound might be breaking down from the initial structure into this 292, and we are not able to see the original mass fragment. And this actually ended up being what we saw. So when we looked back into our data, we found this compound, which is 6,2-FTUCA. So similar to what they found, but 2 CF2 units shorter. and it had not only the same retention time as the snowflake, but it also had the exact same peak at 292.98306. The reason that this one was originally thrown out was because in the MS2 spectra, we don't actually have a matching base peak or M-H peak. And in many cases, this means that the structure is not valid, or it might be something else that is breaking down. However, in this case, we suspect that it might be in-source fragmentation of this compound into the 292 peak that then breaks down in the MS2 spectra. So to confirm this sample, what we ended up doing was buying a reference standard of 6,2-FTUCA, and what we can see is on the right, the reference standard matches both retention time, and we only see this 292 peak. We do not see the actual mass of 356, and the breakdown pattern is also consistent across. So this allowed us to build a calibration curve and actually quantify some of our samples. We were able to confirm this compound in 7 different samples ranging from 0.78 to 127 nanograms per gram. These 7 samples span all 4 food contact material types and as well food types that we tested, being one of those 8 that we saw in all 4 previously when we looked at the total features. This compound was also found in both popcorn bags, food bags for pets, and in French fry materials or in samples from Spain. We also wanted to take these concentrations and compare them to the targeted data that Yelena had previously presented. When we look at the comparison, what we see is over half of our samples actually have larger concentrations of just this one compound than the sum of the 34 targeted PFAS that she looked for in her work. We also saw 2 interesting correlations between 6,2-FTUCA and 6,2-DPOP, which was found in all of the samples where this compound was present, and as well with the total oxidizable precursor assay, which, if you missed, Yelena talked about, and is basically an oxidation process which breaks down all of the potential precursors in a sample, and then you measure the final terminal PFAS products, and the difference between your pre and post gives you a potential amount of precursors. So both of these lines of evidence are leading us to believe that this 6,2-FTUCA might correlate with both the 6,2-DPOP and give us an idea that the top analysis is measuring potentially some of this concentration. We ended up looking into the literature. What we found was 6,2-DPOP actually breaks down into not only 6,2-FTUCA, the compound that we ended up finding, but also the same terminal PFAS that were found in a lot of our samples. These compounds here, the 4 that are highlighted, were basically all found in the samples that we looked at, and this lends further evidence for not only this confirming of the compound that we found, but also that the top analysis can be used to potentially target which samples might be needed for further analysis in future work. One interesting fact to note about this data is that only around 20% of the top analysis is actually explained by this compound 6,2-FTUCA. So we attempted to use fluorine NMR to try and explain or find out some of the other compounds that might be present within these precursors that are creating the breakdown products. At this time, we haven't been able to really glean too much off of this, but the fluorine NMR is a very interesting and upcoming approach that can help us explain the total PFAS, and this tall line all the way on the left actually indicates there might be some TFA or trifluoroacetic acid in the sample as well, which is a compound that is actually too short to measure with a lot of traditional targeted approaches. So this kind of wraps up our first case study looking into this interesting short chain kind of precursor compound. But now we're going to jump into maybe some more traditional legacy PFAS. Long chain PFCAs are some of the original PFAS that were measured in the environment and have been shown to bioaccumulate in a lot of fish species and including a lot of mammals. Because of these reasons, the Canadian government recently added PFOA, which is a 8 long carbon chain, and then all of those chains longer, so C9 and above, to their toxic substances list to remove these from commerce due to their impact on the environment. Now, what this allows us to use is an interesting quirk in the Cofton graph, which is the mass over carbon compared to mass defect over carbon. So on the left, you see all of our data, all of the potential features, and that red box is based on that negative mass defect and as well the range of masses for typical PFAS, the box where some PFAS might be found. Now, if we blow that up on the right and filter out using all of the filters that we talked about previously, what we end up finding is a very interesting line of PFCAs. So now 5 of these are ones that have been previously confirmed with targeted analysis. So that's PFOA, PFNA, PFDA. These are the 8, 9, 10, and 11 carbon long chain PFCAs. But there were 5 other compounds in there that we had not actually quantified yet using our targeted method. So we jumped over to non-target. And what we ended up finding was the 15, 16, 17, 18, and 19 long PFCAs in this one sample. Now this is all in one foil sample, and we initially just were able to find up to the C19. Now the reason for that is actually when we ran our samples initially, we only went up to a master charge of 1,000. The reason for this is in all of the lists that we used, so the PFAS suspect lists, over 95% of the compounds that are in those lists are below master charge 1,000. But there are longer chain PFCAs. So we ended up doing another analysis on this sample, extending our reach up to around 1,300 master charge. And we ended up finding even more ultra long chain PFCAs, including the 20, 21, 22, 23, and 24, including a peak for the 25, but the 25 one was small enough that we couldn't quantify and say that it was actually there. What's interesting is the last 3 of these, the 22, 23, and 24, aren't even in any of these lists that are being used for suspect screening of a lot of PFCAs. And so not only did we end up finding all of these, we also were able to confirm them with analytical standards. Now, unfortunately, we weren't able to confirm all of them. We could only purchase around 3, so that's the C15, 16, and 18. But both the MS2 breakdown pattern, which is shown on top, the retention times, and the peak shapes matched well enough for us to say that these are these long chains, and then we built calibration curves and utilized these standards to then quantify all of the samples. We quantified these 3 compounds directly, and then we were able to semi-quantitatively get concentrations for the other ones using these calibration curves. And what we ended up seeing is when we combine our non-target data with the targeted data, we actually see all the way from C5, so a 5 carbon chain, to 24 carbons long. Every one in between has a quantifiable and measurable amount in this foil sample. And the most interesting thing that we were able to see was actually the final 2, the C23 and 24. Not only have they never been measured in food contact materials before, the only other place we could find them being measured was actually in ski wax. So this was a really interesting finding and a really interesting use of not just looking for the compounds that you see in your output, but also thinking chemically and thinking with your organic chemistry background, kind of what else might be related to that, and using that knowledge to extend your reach to look for more compounds. And with that, I'm finished. That's all I've got. I'd really like to thank SciEx for having me and allowing me to present this really interesting research with everyone here. I'd like to thank NIFA for providing the money for this grant. I'd especially like to thank Dr. Yelena Sapochnikova for giving me this opportunity and working with me through all of this research and all of the data collection and analysis, and as well Dr. Reagan Taylor, who really did a lot of the initial work on the workflow development and then passed a lot of that on to me where I finished up this project, and it really was a collaborative effort for all of us. If there are any questions, I believe there is question time at the end of this. If you are unable to get me there or just want to ask me something more in depth, please hit me up at one of my emails, but I do think my USDA one might be deleted at that point as my internship is finished. I also don't want to forget to thank both ORISE and Baylor University for giving me a lot of opportunities and helping with funding for all of this research. And yeah, with that, I'm off to drive back to Texas. Have a good rest of the summit.